Hello and welcome to this video where today we're looking at wave-particle duality. Now in a previous video we had a look at the photoelectric effect, which is this thing here, where we shine light onto a metal and it causes this metal to emit photoelectrons. So this photoelectric effect basically showed us that light is made up of photons. So that when we define a photon to be the smallest discrete part of the electromagnetic spectrum. So these photons really we can think of as particles of light. So this photoelectric effect basically tells us that light is made up of particles, and these particles are called photons. On the other hand, we've also got lots of evidence that light is also made up of waves, because light, like any other wave, it's reflected, which is one thing that waves do. Light's also refracted, which is a wave effect, so we don't get particles, for example, refracting, and light is also diffracted as well. Diffracted. So when we've been diffracted, if we cast our mind back to GCSE physics, if we have a wave that's passing along here, this way, and these things here are wavefronts, so you can imagine if we think about a light wave, for example, like this, if we think about drawing a line whenever we get a peak like this, then these things here, these things are called wavefronts, and they correspond, for example, to a peak like this. So these wavefronts here are exactly one wavelength apart, because the distance between a peak and a peak is a wavelength. Now if we take this wave and we pass it through a gap, what we see is diffraction. And if you remember GCSE physics, what happens is a wave spreads out like something like this. It's still got exactly the same wavelength, but instead of going in a straight line now, it spreads out in lots of different directions. So the wave comes over here, and over here, and over here, etc. Now this is only seen if the gap that the wave is passing through is roughly the same size as the wavelength of the wave. So if the gap's really big, then we don't see any diffraction effects. If the gap's really small, then really no wave gets through and we don't really see it. So this effect is maximized when this gap is the same size as the wavelength. Now, if this carries on, as we'll see in Unit 2, that these waves traveling in different directions and traveling at different lengths kind of interfere with each other, and what we end up with is, if we had a screen here that detected how bright the light was at certain points, we'd end up with a bright bit here, so this would be bright, and then here we'd end up with a dark bit, and also on this side would be a dark part, and then up here we'd end up with another bright bit. Bright, and my pen's not working, bright, like that, and also you'd end up with a bright bit there. So bright, dark, bright, dark, bright, and it'd carry on like that because of the way that the waves sort of interfering with itself as it passes, as it's being diffracted. Now this is only a wave effect, so this can only happen if light is a wave. So we've got two very strange kind of conflicting things going on here. We've got one set of experiments that show that light is made of particles because it's made up of photons, and that must be the case because wave theory can't explain the photoelectric effect. But equally, we've got some experiments that show that light is a wave, because this effect only happens with waves. Because if, for example, this was made of particles, for example, if we had really big particles and it tried to get through the gap, this is too big. So if we had a stream of particles where the gap's really small compared to the size of the particles, this couldn't get through, so you see nothing over here. If you have particles that, on the other hand, that are really small compared to the size of the gap, then they would travel along, and you'd only see them here. So if you had a detector that detected these particles, you would see basically the particles here, but you wouldn't see any up here and up here, which is what's happening when the light passes through here. Some of the light's being diffracted along here. So this can't be explained if light is a particle. So there's something strange going on, because at some points light's behaving like a wave, and some points light's behaving a bit like a particle. Now in 1924, a scientist called Louis de Broglie basically made a kind of a startling suggestion, really. He basically said, well, if light can be both a particle and a wave, depending upon how it's traveling or what it's interacting with, then maybe everything else is too. And he did some calculations and he came up with an equation which links the wavelength with the speed that a particle travels at. So if, for example, we have an electron, we could say an electron has a certain wavelength, and this thing here is called the de Broglie. It's spelled de Broglie, but it's actually the de Broglie wavelength, which is measured in meters. So that's your de Broglie wavelength, which is measured in meters. This is Planck's constant, which we've seen before. So that's Planck's constant, which is our 6.63 times 10 to the minus 34 joule seconds. M is the mass of the particle that we're looking at, and V is the velocity. And if we remember again back to our GCSE physics, momentum is equal to mv. So if that's that can be, sometimes this equation is written as momentum instead of having the velocity in it. So sometimes it's written as the wavelength is equal to h over p. So if it's p, it means momentum, but momentum is just equal to mass times velocity, which is where this thing comes from. The mass must be in kilograms, and the velocity must be in meters per second, like that. So if we have a particle, for example, that's travelling along and it encounters a gap which is approximately the same size as its wavelength, then the particle, the wave nature of the particle will cause it to diffract. So you could have, for example, electrons travelling along that normally we think of particles. If, however, it encounters a gap of the wavelength of its wave, then we will see an electron, which we normally think of as a particle, behaving like a wave, and so it diffracts. So we can do some calculations with this equation over here. So let's try and work out the wavelength of somebody that's 70 kilograms walking at 1 meter per second. So a couple of steps. First of all, we write down our equation like that. So and then we put our numbers in. So h is 6.63 times 10 to the power of minus 34. Divided by the mass, well, the mass is 70 kilograms, multiplied by the velocity, well, the velocity is 1 meter per second, and if we do that on a calculator, we end up with 9.5 times 10 to the power of minus 36 meters, like that. Now that's incredibly small. That's very, very tiny, and you never ever encounter gaps that are that small, which is why you never see a person diffract. Which in itself would be a very strange thing. But the reason that you don't see really, really big things diffract is simply because they don't encounter gaps that are as small as the wavelength that they have. However, if we look at very particles that have got a very small mass that travel very quickly, then it could mean we end up with a much bigger wavelength, and therefore we actually see diffraction. So let's do a second example. Let's have a look at the wavelength of this electron. So again, we'll write down our equation, h over mv. Again, Planck's constant, 6.63 times 10 to minus 34, divided by the mass. Well, the mass of an electron, if you look at your data sheet, is 9.11 times 10 to minus 31 kilograms, multiplied by the velocity. Well, the velocity is this, 7 times 10 to the 6. And again, if we do this on our calculator, we end up with 1 times 10 to the minus 10 meters. Well, again, that looks really small, but whenever we look at the distance between atoms, so if we take, for example, if we take something like graphite, and we look at the distance between atoms in a sheet of graphite, then the distance between here and here, the gap is of the order something like 1 times 10 to the minus 10 meters. In other words, if we shone these electrons through this graphite sheet, because this gap is the same size as the wavelength, we should see electrons diffract. So that's the theory he came up with in 1924, and then obviously when people come up with a theory, we go away and we have a look to see actually whether it's true. And actually people found that this really did happen, because they took electrons, so they took some electrons just simply from an electron gun, sort of like the old TVs that people used to have, and they fired them at basically a sheet of atoms. And so this consists of a sheet of atoms like this, And what they saw was that what should have happened if electrons were particles is they would have come straight through, just like we saw in at the beginning of this video. And what they should see is simply the electrons being deposited here if they were particles. But actually what they saw is they saw that they spread out. So they saw all those electrons up here and up here. And actually what they saw is as the electrons passed through these gaps, what they found is that the electrons showed these bright and then dark and then bright and then dark patterns, exactly like light does when it shone through a gap. Now because there are lots of gaps here, we end up with kind of a 3D pattern, so we end up with something like this. So this really bright part in the middle shows us this part here. So this is the bit where most of the electrons basically they're coming straight through. And then there's a dark bit which corresponds to our dark part here and here. And then we see a light bit again, so that corresponds to this light bit there. So that's a light part, and that's a light part where the waves have constructively interfered with each other. And then you get another dark part, and then another light part, and so on, just like we did when we shone light through a gap. So this was conclusive proof that electrons diffract. So electrons, which we normally think of particles, they diffract. And actually this has been done with a number of different particles, so we now know that, for example, neutrons diffract, and they need a much smaller gap because they have a much bigger mass for the same speed. But again, neutrons diffract and protons diffract. So the final thing we need to say is that if we have particles of shorter wavelength, then if we sped these electrons up, if we made these electrons move faster, then our wavelength would get bigger. So the difference between the gap and the wavelength would change, and so your diffraction would change. And so what you see is if we change the speed of these things, then the gaps between this ring, for example, and this center ring will change, and actually it will get closer. If you slow the electrons down, then the gaps will get bigger. But this shows that electrons behave sometimes like waves. So this is what wave-particle duality is. It basically says that particles, which includes light, electrons, protons, neutrons, any very small particles, can sometimes behave like a particle. Now, electrons, protons, and neutrons, we imagine are particles, but that also happens with light, and the particles of light are photons. But sometimes they can behave like waves. So if we pass electrons through a gap or neutrons through a gap or something like that, where the gap is essentially the same size as the wavelength, then they will behave like a wave. But other times we see them behave like particles. So that's what wave-particle duality is. Sometimes these things behave like waves, and sometimes these things behave like particles. So that's really it for wave-particle duality. Thank you very much for watching, and I will see you again soon.